Welcome to Spring LIB.
All right, so two protons are moving towards each other in the rest frame of a lab. So the lab is at rest. Protons moving towards each other with equal but opposite velocity of 0.99 c. So let's start by defining a convention here. Let's call this side positive and the other side negative. And let's call this proton 1 and this proton 2. And so we've just set a convention here. You could, of course, switch this around and you'd get equivalent answers. But this is for ease of calculation here. We're calling the direction of motion of proton 2 to be positive and the other one to be the other direction to be negative. Okay? And so to start off, you need the momentum of a proton. And the momentum can get from equation 26-4 in the book, which says that P will be equal to gamma mv, okay? So that is just mv over square root of 1 minus v squared over c squared. And mass is the same for both protons. They're moving at the same velocity, just with a different sign. So momentum will be equal and opposite, all right? And so this will be the same magnitude of momentum for both protons. And so mass of a proton, we know from the book, is 938 MeV per c squared, and it's okay to keep it in these units. Velocity is 0.99 c divided by square root of 1 minus 0.99 quantity squared. That's because v equals 0.99 c, so all we have to do is square the 0.99. And what we get, lo and behold, is 6585 MeV per c, because one of the c's here cancel. And it's okay to keep these in, keep it in these units. So that's part A, and this is the same. So this magnitude is the same for both protons. In part B, we note that P1 will be exactly equal to the negative of P2, because remember the magnitudes are equal, but while this one has a positive momentum, proton 2, proton 1 will have a negative momentum because of traveling in the exact opposite direction. So this means that total momentum, P tot, equals, you're adding them up, P1 plus P2, which means P1 minus P1, and that's 0. So total net momentum is 0. Okay. In part C, we use the relativistic addition of velocities formula, the notorious u equals v plus u prime over 1 plus vu prime over c squared. And so the problem here is to define or choose your reference frames. Okay? And so the reference frames we will choose here is S prime is the reference frame of the lab, which is a frame at rest. S will be the reference frame of proton 2. So this one over here. And this means that V will be the velocity of the lab with respect to or relative to proton 1. U prime will be the velocity of proton 2 with respect to the lab, which is the rest frame. And so what we're going to find, u, is the velocity of proton 2 with respect to proton 1. Okay? And so let's work out what they are. V, the velocity of lab with respect to 1, will be 0.99 c. And this is because, remember, we've chosen this direction to be positive. And so the lab, which is at rest, we'll see. So for the lab, which is at rest, and if you're measuring from proton 1, it would appear that the lab moves towards it with its velocity. And moving towards it means it's moving in the positive direction, right? So you have a velocity of 0.99 c in the positive direction. That is why it's 0.99 c. And u prime, which is velocity of 2 with respect to lab, is also 0.99 c positive, which is because in the stationary frame of the lab, 2 is moving towards it, which is in the positive direction, with, of course, its speed 0.99 c. And so all we have to do now is find the velocity of 2 with respect to 1. And so we plug in the numbers for v and for u. The denominator goes there, 0.99 times 0.99. Note that there's no c over here because the c squared on the denominator here cancels out with the c from the 0.99s there. And so what you end up with is 1.98 c over 1.9801. And so that's very, very close to the speed of light. It's 0.99995 times the speed of light. Okay. And so once you have that u, you can get your gamma factor, which we'll use in a second. So gamma is 1 over square root of 1 minus, remember, v squared over u squared, so v squared over c squared. V in this case is u, so 1 minus 0.99995 squared, right? And that's equal to approximately 100. And then finally, we use the momentum equation again. So in the reference frame of proton 2, the momentum is gamma mv, or in this case u, which is 100 times the rest mass of a proton, which is 1.67 times 10 to the negative 27 kilograms, times the velocity, which is 0.99995 times the speed of light. This will be in meters per second. And that's 3 times 10 to the 8 meters per second. And we could also actually write this as 938 MeV per c squared, because remember, the energy of the rest energy of a proton is 938 MeV, and so you divide that by c squared using the famous E equals mc squared. You get 938 MeV per c squared of the rest mass. And so I think it'd be a lot easier to write it down in this form, and that way you have one of the c's canceling out with that c. What you're left with is 93,400 MeV per c. And this is actually about 93.4 GeV per c finally, because 1 GeV is 1,000 MeVs. So that's your momentum. And there's that.